Da-da-da. I think did I talk about pooling yesterday too? I think I might have quite a bit. Can you remind me? Did we talk about pooling yesterday? Um, Pooling in tests. Yeah, I think we did. But let's clarify. Pooling is something that happens when you essentially you combine data together um, from sort of separate samples. So typically, if you took two samples from two different populations, then those should be treated as separate samples. However, if you have some assumption that gives you a reason to combine those samples into, say, like one large sample, then you should do that, right? It's good to have larger samples. We know bigger sample sizes are good, right? Why are bigger sample sizes good? Well, intuitively, they were good because it just meant you had more data. But mathematically, a large sample size is good because it reduces something. What does a large sample size do? It reduces what's a V word? What's the V word? It's yes, I see Doreen answering with VAR. It reduces variation, right? Or it reduces, we'll see, variability in, say, a sampling distribution. So when we have sampling distributions, right, if you have a very small sample size, there's going to be lots of variability in that distribution. However, for smaller sample sizes, you're going to get less variability, and you start getting things that will be taller in the center and narrower, and sort of squeezing things down. So large sample sizes are good. And so if we can pool to multiple samples together and to treat them as one large sample, that's a great thing, right? So the key, of course, when we were doing population proportions, we had this null hypothesis that say the proportion from one population is the same as the other, right? So I think in the examples, one of the examples we were talking about yesterday, we were talking about like seniors and freshmen, or like males versus females. But like, say you had like a population of males and you had a population of females, right? And then you took samples separately from each, and you calculated some, proportion. This was like the proportion of males that had some characteristic. This is the proportion of females that have a characteristic. And this is the true parameter. But you took a sample to estimate this, and you don't know what this is, So you got this sample, this little p hat, right? And this p hat helps you try to figure out what p is, and this would be p hat m. And you took some sample from the females, and it was p hat f, and then you use that to try to figure out what pf is. The key idea is technically these samples were from different groups, but if I make an assumption that this proportion here should be exactly the same, this proportion should be exactly the same as this one, that they should be equal, then great. Then if they're supposed to be equal anyways, then I can take all the evidence I have here of what p is, right? And we could say if they're both equal and they're both equal to just some value p, then if I want to take this information about what p is and what this information about p is, I can combine it all together. So p, right, a better estimate for p would be the total sample size of the males, right, plus the total sample size of the females. And in the numerator, the number of successes I had in the males, and here the number of successes I had in the females, right? So it's just getting a better estimate based on a larger sample size. And of course, that's all justified by this assumption of equality there, right? And so that when we use this is when we have that assumption. That why don't we use this when we're making a confidence interval? Because in a confidence interval, there's in a confidence interval, there is no assumption, right? There is no assumptions at all. We don't make any assumptions in a confidence interval, except for maybe potentially about the conditions that allow us to make a particular confidence interval. There's no assumptions about the actual values themselves. It's all just based on sample stats. So we're not going to ever have any pooling, right? Combining multiple samples together into a large sample, unless we're not going to do any of that pooling without some kind of fundamental assumption. So it's actually an interesting thing too, because and I'll point this out now. What we're going to learn to do a some one sample, or excuse me, two sample T procedures. So for instance, if you today you're going to learn to do a two sample T test, and if you click on it and you go down, you're going to see like you put in sample mean from a first population, sample mean from a second, sample size, then another sample mean, another sample standard deviation, another n. Do it. And then all of a sudden the calculator is going to say something weird about pooling. It actually gives you an option. It's going to say pool, no or yes. And let me ask you this. If you just had to guess, are we going to say yes to pooling or no to pooling when our calculator asks us to here? If anyone want to take a guess. I mean, this is obviously just a guess. Harry coming in with a yes. Let's see. Anyone else taking a guess? Let's see. Doreen says yes. Anyone else guessing? Kate says yes. Harry says yes. All these beautiful yeses so far. Evan, I like that. Sure, why the heck not? All right, let me tell you. The answer is when the calculator asks you to pool, your answer will be no. Absolutely not. If your calculator, I know, isn't that crazy? If you're doing a two sample t-test and your calculator says, hey, you want to pool, your answer is always going to be no. And in fact, your calculator should default to no. You'll have to go out of your way to say yes. So don't do that. And here's just a way to remember. Like, so in a proportion, you're not even given the choice. The calculator knows that you have to pool and you do pool. Here, you're given a choice. And if you're given a choice, do you calculate a p-value by pooling? The answer is no. Do not pee in a pool. No peeing in the pool. All right, so beautiful. Kate, I like why you're asking. Why did they give you the option? Doreen, why? Well, because I'll tell you the reason why I say no is because this course is called AP Statistics. AP Statistics is not the same as statistics. There's actually very good reasons to pool and say yes in a context that we will never have in AP Stat. I'm going to explain to you now why we pool here. Why would we pool things together for a proportion, but not pool when we do a t-test? And I will tell you exactly why. So it has to do with what our assumption is, right? So you're going to learn in videos today that you're going to do, we're going to do these similar things about what am I trying to say? The two sample T procedures for a mean instead of just for a proportion. So let's do an example similar to yesterday. Let's say we had, once again, seniors here, and here we have freshmen, right? And here's the freshmen. And yesterday, the variable that we were looking at was P equals the proportion of students who have book bags that weigh over 10 pounds. Today, let's change it to let's say the average weight of the book bags, right? So here, this is the average weight. So let's define mu. We'll say mu equals the true mean weight of people's book bags, right? And so here's the weight of the seniors bag. We'll call that mu S. Here's the average of the freshman's bag. We'll call that mu F, right? Okay, so once again, we'll take a sample and we'll get a sample mean and we'll get a sample standard deviation. And here we'll get another sample mean from the freshman and a sample standard deviation from the freshman. And so, of course, the reason that we're going to be doing T procedures here is because everything is based on sample standard deviations as opposed to population standard deviations. Now, all right, so our null hypothesis, you can probably guess what will be our null hypothesis between seniors and freshmen about their average weight of their book bags. What will we say? Well, we're going to say the average weight of a senior's book bag is what compared to the average weight of a freshman's book bag? What will be our null hypothesis? What symbol will we connect these two with? You guys know. As a null hypothesis, we will use equals. Yes, be careful there. Null hypothesis is always equal. Always assume equality. The alternative is that now a couple of people chimed in less than before. I think that would make sense as the alternative hypothesis. We'd try to prove that the average weight of a senior's book bag is less than the average weight of a freshman's book bag. So that's cool, right? And of course, just like we saw in our other in our other lesson that we'll turn this into a difference, right? So this null hypothesis will end up becoming mu s minus mu f is equal to 0. And the alternative hypothesis will end up becoming mu s minus mu f is less than 0, right? So we're taking this inequality statement and turning it into a statement about differences. So that's nice, nothing new. Okay, but remember, the whole thing, this is kind of an intro to things that you're going to be learning in your online video lectures today. But remember, the whole reason I brought here was to talk about pooling and why we pool here for proportion, but we're not going to pool here. Well, pooling, right, has to do with some assumption of equality. And actually, we do have an assumption here that these two means are equal. So you might say, I have this assumption that this mean is equal to this mean. Maybe I should pool. Be careful. Pooling for a T procedure means we need to be able to assume that sigma 1 is equal to sigma 2, right? So check it out. When the pooling that could potentially happen for a T procedure is entirely based on assuming that the standard deviation of your first population is equal to the standard deviation of your second population. Now, let me ask you this. When we make our null hypothesis that mu s is equal to mu f, does that also mean that sigma s is equal to sigma f? Is that the null hypothesis? The answer is no, right? In a t-test, the t-test, right, there's no assumption in general about sigma, right? It's only about mu, right? That our null hypothesis only makes an assumption about the two averages of the two population. It makes no assumption about what the population standard deviations are. And so in this instance, since we don't have any reason to assume that the standard deviations are going to be the same, we will never assume that they're going to be the same, right? This is actually more of kind of like how we, another thing you're going to hear is discussions of like conservative approaches and stuff like that in some of these videos. But this is like a very safe bet, right? Your math will end up getting much simpler if we can make this assumption right here, but it's also usually a false assumption, right? It's very rare. This is extraordinarily rare. This is very rare that these two population standard deviations would be equal. And so we'll never make that assumption. So when your calculator says, do you want to pool? The answer is 9, because when your calculator is asking, it's really saying, do you want to assume that the population standard deviation in population 1 is the same as the population standard deviation of population 2? So when your calculator says, do you want to pool? What's your answer going to be? All right, you tell me. What's your answer going to be when the calculator says, do you want to pool? The answer is no. No, do not pool. Cool beans. Now, just out of curiosity, is anyone curious about what would happen if we did pool? Anthony, you got another class? I'm happy you have another class. Go to your other class. Oh, he's gone already. He was in a hurry. Maybe that's Harkness. He's jumping into Harkness maybe or something. I don't know. But what actually happens, and this is crazy, the craziest thing that you're going to learn in today's lesson, and I'll give you a preview of it, has to do with the thing that made working with a T distribution a little bit more challenging than working with a normal distribution. You guys remember that the normal distribution, right, is a fixed shape, right? And that if you were to go out 1, 2, 3 standard deviations from the mean, you always know what proportions are an interval. So if you went out 2 standard deviations from the mean, about what percent is 2 standard deviations from the mean in a normal distribution? How much should I shade in approximately? Right, Doreen chimed in. You guys surely remember that within 2 standard deviations is approximately 95%, right? And of course, now we know, to be more precise, 95% is really 1.96 standard deviations and all that. But the normal distribution, right? This is a normal distribution 0, 1. It's fixed, right? If you want to know how far out do you go for 95%, remember when we talked about this, especially for confidence levels, like if you want to get to 95% confidence, you know that you could go to a z-score of 1.960 and you'd be good to go. Does that work with the t-distribution? Was that the case for the t-distribution? Was the t-distribution fixed just like the normal distribution? Oh, no, Dominic's chiming in. You're correct, Dominic, right? No, it's not fixed, right? Evan, I see you. Yes, beautiful, right? In the t-distribution, for different sort of parameter of the t-distribution, you might end up having something that's like chunky, like on the edges like that, like really large tails, right? Or as your parameters change, then this guy will come lower here and have more proportions, kind of like this. Anyway, this is terrible. I'm embarrassed by this drawing. That makes me a little sad. But the idea is the shape is changing, right? The t-distribution, right, is this family, right? It's this happy family of different curves, right? And who can tell me what is the thing that changes develops the shape of these distributions? What do we look at that all of a sudden determines what this guy's going to come out to? Aha, Kate chimes in correctly. First, it's the degree of freedom. Right? Very dramatic, right? And so the degree of freedom changes. So this really like fat-tailed one is going to have a small degree of freedom, like degree of freedom of something like 2, and then like one that's taller and skinnier and it looks more like the normal distribution will have a higher degree of freedom, like, I don't know, degree of freedom of 30 or 60 or 100. And if you remember that the t distribution with degree of freedom that approaches infinity is actually going to be, is the what, right? It's the z distribution, right? It's the normal distribution. And so eventually the t distribution will shift into a normal. Harry, what should you cook for lunch? I'm going to go with grilled cheese. How's that sound? I don't even know. What do you have in your house? You'll have to let me know. But we can do a little chop challenge. You tell me you tell me 4 ingredients you have, and then you have to make something with it. It'll be good times. But the instant noodles, there you go. Is that one of the elements for the chop challenge, or is that Kate, or is that I don't know. I'll come up with a plan for you. I'll come up with 4 ingredients, see if you have them, and you can see what you can come up with, Harry. But anyway, let me go back, right? So remember, we were talking about pooling with T procedures, and I was trying to say we don't make this assumption. What would pooling do? Well, what pooling actually does is it changes how we find the degree of freedom. So when we do these 2 sample procedures, right, you're going to have 2 sample means, and you're going to have 2 sample standard deviations, and you're going to have 2 sample sizes, right? So you're going to have, like, in your first sample, say you took a sample of seniors and you had like 42 seniors in your sample, and say in your second sample, your sample of freshmen, you only got 36, right? And then you'd say, all right, in this scenario for my 2 sample t-test, right, what's going to be my degree of freedom, right? What would I do? Well, you're going to see that that this starts to get really complicated, right? When we did a 1 sample t-test for a 1 sample, then we knew that the degree of freedom was just what? Who can remind us what's the degree of freedom if you have a 1 sample procedure? It's super easy. It's just what? N, yeah, Doreen chimes in, N minus 1, right? Evan chimes in, beautiful, N minus 1, if it's a 1 sample. Now, this is a 2 sample test. You have 2 different samples. What will be the degree of freedom here? Like what will be the degree of freedom that determines the t distribution that will determine our critical value for a confidence interval or determine the shape of the distribution for calculating a p-value? Like what will we be? You don't know, right? You need to be told. Like you could take some guesses and hypotheses about what it would be, but you're going to see it actually gets really, really crazy and complicated. There's actually a couple of approaches. You're going to learn in the videos today that there's first an approach that's called the conservative approach. And the conservative approach means basically pick the smaller one. Pick the smaller DF. So if you look at this guy, the degree of freedom that would come from, if you just looked at one sample in entire isolation from any of the others, then the degree of freedom for this guy would be 41. Right? And if you looked at this sample entirely in isolation from the other, then its degree of freedom would seem to be 35. And so this conservative approach would just be like, oh, pick which one's smaller, 35. So that would become the degree of freedom for that particular scenario. That's the conservative approach. But this conservative approach is like just a safe bet if you can't do fancy calculations. There's actually going to be a crazy formula that you don't have to know. And I'm showing it to you. In fact, let me see here. Let me see if I have it's too complicated for me to even just write down for you. Where do I have my paper with the formula on it? I'm trying to find it. So, here it is. This is a preview from the videos, and I have it kind of crossed out. But this is the formula for the degree of freedom. It's crazy, right? The formula involves the standard deviations of each of your two samples, involves your separate sample sizes, and it's a crazy formula, right? So this formula you do not need to know. All you need to know is that there is a formula that exists, and what happens is that and that's why you get a decimal, Kate. That's why you get a decimal for your degree of freedom, because this will virtually never come out to a whole number. This is always going to come out to some weird decimal. Now, the complete derivation of this formula, I still have not fully grasped exactly why this formula gives you a reasonable estimate of the degree of freedom. But this always gives you a number that's bigger than the conservative approach. So the conservative approach says 35. The formula is always going to give you more freedom than the conservative approach. You'll always see that, right? My video just got really fuzzy there. Hope you guys can see what's going on. So that's the idea. So there's a crazy formula. Now, here's the cool, fun thing. So this formula is ugly, but something that you'll actually see at the end of the second video, and I briefly don't prove this, but I say it, that remember, this is going back to pooling, that if you were allowed to pool, if we knew that we could pool, then the formula, that this crazy formula, this nutty formula right here, if you pool, simplifies amazingly. And the formula simplifies to, if you pool, to N1 minus 1 plus N2 minus 1. In other words, N1 plus N2 minus 2, right? So if you were to pool, that crazy formula gets ridiculously simple. You would just basically add the two separate degrees of freedoms. So, and that sort of would be the maximum case, right? So in other words, the degree of freedom that you'll get from this formula when the calculator does it will always be bigger than the smallest degree of freedom here. But it'll always be less than simply adding these up. So if we pooled, the degree of freedom would have been 41 plus 35 is 76 minus 2, that would have been 74. If you were allowed to pool, which we're never allowed to pool, the degree of freedom would have just been 74. You'll see that what the calculator comes up with that crazy formula is always going to be something less than that number. So Kate, let's see here. Is there a non-conservative approach in which you pick the bigger one? No. Really, the only options you pick are either going to be the super conservative approach, pick the smaller of those two, right? Or the formula itself. This whole pooling thing that this is just like, this is not technically relevant to AP Stat. I'm telling you about it because I'm trying to enrich your lives, but we'll never, ever use that one. In practice, the best degree of freedom will always come from this formula. And that's what the calculator does, right? So if I made up, for instance, here, if I just made up statistics, let's say I sampled, what did I say here? I said 42 seniors. And let's say the average weight of their bags was something like, I don't know, 7.8 pounds. And the standard deviation was something like, I don't know, like, let's say it was really heavily skewed to the right. So maybe like 5.2 pounds. Let's make the sample. I'm just making stuff up. How about 6.4 and 5.2 heavily skewed to the right? And then here I said 36 freshmen. And whoa, I'm messing this up. No, sample mean 1, let's say 6.4, 5.2, heavily skewed right. Sample size was 42. Then here, sample mean 2. Let's make something up. Average weight of a freshman's bag, let's say it was something like 11.5 pounds. Let's say it had a standard deviation of something kind of big as well too, let's say 6 pounds, and the sample size there was 36. If I did a test that these two things simply are not equal, I guarantee you we're going to get significant evidence. If I hit no to pooling and I hit calculate, then notice the degree of freedom is 69.856. It tells it to you right there. And that's what the calculator figured using this formula. You didn't have to do it. It just does it for you. And you just know that it's right. Now, if I pool, just so you see what happens, if I go to a 2-sample t-test and I say, oh, pooling, Mr. Zach said never to pool, but let's just say we did, then if you hit calculate, you got degree of freedom of 76. Why does it say 76? It's supposed to be N1 plus N2 minus 2. Now I'm confuzzled, actually. That's interesting. That's something I need to think about. I don't have a good answer for why it said 76. I was certain it would say 74, unless I didn't add right. No, I don't know. Did I put in the sample sizes correctly? 42, 36. Oh, I put in the sample sizes wrong. Sample sizes. I know why. I'm so dumb. You know what, guys? I just realized I know why it said 76, because here I added the degree of freedoms and I subtracted 2 when I was trying to demonstrate what this formula was. I didn't add 42 plus 36. 42 plus 36 is 78, and then 78 minus 2 is 70. That's why. Thank you, Dorian. You noticed how dumb I am. I accidentally added the 2 degree of freedoms and subtracted 2. Supposed to add the 2 sample sizes, subtract 2. I just wasn't paying attention to which numbers were what. So anyway, that got really confusing for me there for a second. But yeah, notice that the degree of freedom, when you pooled, ended up just being the sum of the sample sizes minus 2. But we'll never do that, right? Never, ever do that. We'll always say we will not pool. So pool no, always say no. I'm going to switch it back so I don't accidentally say yes some future time, right? So 69.8 ends up being less than 76, but definitely way more than conservative approach. So anyway, that's the only really weird stuff. And that'll, I do explain that in the video lessons as well too, but you guys are seeing it here and hope that works. So yeah, any other questions about statistics or about the stuff I just kind of showed you here today? Let's see if you have any questions. Harry, we'll get back to you and your lunch in a minute, but any other questions? Let's see here. Would you round normally for the decimal? In terms of the decimal, you just keep the decimal as is, right? Just and in practice, I mean, the reality here, I'm switching back to me. In practice, the calculator already did all the math for you. The only way you are going to actually get that degree of freedom is by creating the interval in the calculator already, or by calculating the p-value in the calculator already. So you can just write down the degree of freedom to like 1 decimal place or 2 decimal places just to communicate which degree of freedom the calculator used. But you don't have to actually do anything with it. The calculator already did all the math with it. So it doesn't matter. You can write down whatever. It ultimately doesn't matter, Doreen. It's not up to you to use the degree of freedom in any special way. You just say what the calculator used, if that makes sense. Okay. Let's see here. Any other questions about any of that stuff? I see Anthony joined us again. Welcome back, Anthony. Did a short class. Our classes go way longer. I don't know. What did you miss? Well, you will. I will post. I'll post at least I'll post the mathy portion of this video, and then you'll be able to see what you missed, Anthony. It was me just going in a little bit more detail than I do in some of the videos about pooling with a t-test and degree of freedom in a t-test. So it'll be cool. You got it, man. Anyway, any other questions? I might stop if there's actually I actually want a question, but I might stop the video. If there's no math questions, I'm going to stop the video because really I'm just trying to record the math portions of this for people. But I do have actually, let's see here. I'm gonna shut down the video because I don't see any math questions. Let's stop the recording there.